Happy New Year, everyone, and welcome back. May this year be better than the last. Now that we're back, we're going to begin talking about Chapter 4. In Chapter 4, we're going to be talking about two of the most fundamental mathematical objects that will show up in all the other math classes of various flavors. And those two objects are sets and functions. Now, we've already talked about sets some back in section 2.2, but in this section, when we talk about sets, we're going to go more in depth and talk about some various sorts of set operations that we did not talk about before, like the Cartesian product and the power set, as you will see. We'll talk some more about set notation and various things of that sort. Then we'll talk about the mathematical definition of function, which, as we'll see, differs a bit from the sort of loose definition that shows up in calculus courses. So we'll want to be careful that we have a very precise definition of a function, and then once we have that, we'll try and define the versions of domain and range, and all the various properties that you might want a function to have. So putting these pieces together is going to take a while, and we're going to be going over a lot of definitions so that we can carefully really understand these things in depth. And in fact, when we talk about Chapter 5, which is the last chapter we're going to talk about, which is about cardinalities of infinite sets, it is going to lean as heavily as possible on all the ideas from both of these pieces of this chapter. First, I want to reiterate the definition of a finite set versus an infinite set, as those are terms we're going to talk about a lot in this section. So in particular, when we talk about a set being finite or infinite, we're talking about the number of elements. So there's a particular example where this quite often gets displaced, and that particular example is with open intervals. So this is the set of all the real numbers between 2 and 5, not including 2 and not including 5. It sort of seems in some sense like this should be finite, but this is definitely infinite. Note that is very different than this set, which is definitely finite. But this interval here, remember, this is all the numbers here between 2 and 5. I do want to note that in terms of actually using it in proofs, this definition of infinite, that it doesn't have finitely many elements, is not super helpful. So I'll give you an alternate definition that's just a different way to say the same thing that is useful in doing proofs. So a set A is called infinite if there's a non-repeating, non-terminating list, x1, x2, x3, and so on, of elements of A. This is useful in particular because it lets us actually produce something if we have an infinite set. Namely, we get one of these type of lists. On the other hand, if a set is finite, then its size is some positive integer, or 0 technically, and so we can write the set A as just a list of x1 through xn, where n is the size of the set. It's just the number of elements. So this gives you some idea of what's going to happen in proofs if you have the hypothesis that a set is finite versus if you have the hypothesis that the set is infinite. You're going to get some collection like this most of the time. Let me do a couple proofs that use these definitions. So let's prove that if A and B are infinite sets, then A union B is infinite. Now, just to be clear, if you used this without proving it, I would not complain. I am not going to require you to prove, for example, that the union of two finite sets is finite, but I'm going to show you how you could prove that sort of thing from these definitions, so that when we actually do need to use these definitions, we can. So our proof is going to start by supposing that A and B are infinite sets. And then I'm going to write out the definition of infinite for A. That is to say, since A is infinite, there is a non-repeating, non-terminating list, x1, x2, x3, up to so on and so forth, of elements of A. Non-terminating, to be clear, means it doesn't stop. So in particular, that's what A being infinite means. So what do we have to do to prove that A union B is infinite? Well, by the same definition we just used, we have to prove that there is a non-terminating, non-repeating list of elements of A union B. But, and this is the key, because of the way unions work, this same list is also a list of elements of A union B. And thus, A union B meets the definition of infinite. Now, here is where you might do a little proof detective work and realize that, in fact, we never used the fact that B was infinite. And so, in fact, if we were typing this proof up now, we could actually say, suppose A is infinite, and then the rest of the proof just works verbatim. I don't need to suppose that B is infinite, or finite, or empty, or whatever. It can be any of those things. In particular, the thing I want to draw your attention to in this proof is that this non-repeating, non-terminating list of elements of A union B is most likely not all of the elements of A union B. Note, when I wrote down this definition, I explicitly did not say I wrote down a list of all of the elements of A. I just said that I wrote down a list of some of the elements of A, and that list happened to go on without repeating and without terminating. So you can definitely show a set as infinite without listing all of its elements in some sense. Here's another claim that I think is a little bit intuitive, but that I want to just show you how you would write down this kind of proof, just so we can use the definitions of finite and infinite in practice before we use them in another context. So we're supposing here that A is infinite and B is finite. Since A is infinite, we can write this non-terminating, non-repeating list of elements of A, x1, x2, x3, and so on. And now B is finite, and here's the problem. Some of the elements of B might be in my list. And so what I want to do is I want to collect all of the elements of B that happen to be in my list. Now, because B is finite, this is going to be a finite set, and it may well be quite a bit smaller than B, because perhaps B has some elements in it that aren't in A at all, or maybe there's some elements that are in A and B but don't happen to be in my list. Again, this list of elements is not comprehensive. So here's going to be a finite list of things, and so here is the thing everyone absolutely hates. Which is to say, I now, when I go to write down which elements of B happen to also be in here, I can describe them as x sub something, but now it's x sub something, x sub something, x sub something, and so I actually need a subscript on my subscripts in order to describe this. So again, I've just grabbed basically the indices of the things that showed up in this list that were also in B. And I've arranged it so that IL is the highest index. And so in particular, IL is the maximum of this set. And L, you can deduce, L is the number of elements that are in this set, the intersection of B and this list. Now, I want to note here, this is one of the ways that finiteness is used most often. Namely, finite sets of integers, like I1, I2 through IL, for example, have maximums. So a lot of the time when you go to prove something that has a set being finite as a hypothesis, the way you are going to use that is to either, if it is already a set of integers, note that it has a maximum, or, as in this case, if it is related to a set of integers, then find the maximum of that. But what does all of this mean? This means that if I look at my big long list of x sub i's that show up in A, then there's this finite list of ones that show up in B, and so if I skip ahead in my sequence, x1, x2, x3, to start at x sub I sub L plus 1, and please note this here, this really is one more than the I sub elf index, not I sub L plus 1, which would be undefined. But all I've done here is basically start with my infinite sequence x1, x2, x3, x4, x5, x6, slide it all the way down so that every element of B I've slid off. And now I'm starting at the number after the last element that showed up in B showed up in the list. But because of the way infinity works, this thing is still definitely a non-repeating, non-terminating list. But now, everything in this list is an element of A minus B. But I have now shown you how to make a non-terminating, non-repeating list of elements of A minus B, and so A minus B is infinite. And so these two examples were just to give you a sense of how you apply the hypothesis that a set is infinite and the hypothesis that a set is finite in proofs, because often people have a lot of questions about that. So now let me introduce our first new set operation of this section, which is what we're going to call the power set. So the power set of a set is the set of all subsets of that set. And for the notation, we denote the power set of A by some sort of script P of A. I usually use the mathcal P. So in particular, the power set is always a set of sets. So if you enjoyed all of our sets of sets examples in the previous set section, then you'll enjoy them here as well. So as a first example, let's write down the power set of the set 1, 2, 7. So the power set here is going to be a set of sets that's going to contain every subset of 1, 2, 7. Now, two subsets of 1, 2, 7 that I know are 1, 2, 7 itself and the empty set. In particular, the empty set is a subset of every set, so whenever you go to write down a power set, it is going to have the empty set in it. But there are more subsets here, so the so-called Singleton subsets, that is the subsets with only one element each. And then there's also subsets that have two elements. And so, note, this is itself a single set that has all of those sets as elements. So in particular, the size of 1, 2, 7 is 3, and the size of the power set of 1, 2, 7 is 8. And already you might guess a pattern of how you get from 3 to 8, but I'll leave that a mystery for the moment. Now, the place where this tends to get especially upsetting is when the thing you're taking the power set of already has sets as elements. And so I want to do some examples of that. So first I want to write down the power set of the empty set. That is, what is the set of all the subsets of the empty set? Well, what things are subsets of the empty set? Well, only the empty set. Now, I know what you may be thinking. You may be thinking, so the power set of the empty set is itself. But that is not true, because, and this is an important note, the empty set and the set the empty set are not the same thing. In particular, if you look at the size of the empty set, that is a set of size 0. The empty set contains no elements. Whereas, the set of the empty set actually contains an element, namely the empty set. And so as a result, these two things are very different. And so if you recall back in chapter 2 when I was stressing how important it was to keep track of your notation and when to use parentheses and these set braces and all of these things, it was because we were going to get here where we have to be super careful to distinguish between a set of things and a list of things, or just the thing versus the set of the thing, etc. Now, in hopes of making this clearer, although it might have the opposite effect, let's find the power set of the empty set. That is, what is the power set of this? Well, the empty set is definitely a subset of the set the empty set. But the empty set is also an element of the set the empty set. And so that means this is in fact a subset. And so, in fact, these two things that I said were different before, the empty set and the set of the empty set, those are the two elements of the power set of the empty set. And again, this is the really weird instance that we talked about all the way back in the chapter 2, where here the empty set is both a subset and an element of the set, the empty set, which is very, very rare. Almost always something is going to be at most one of an element or a subset, depending on what kind of thing it is. In this instance, because we're talking about the empty set and things with the empty set are weird, we actually have that the empty set is both, which then leads to both of these things being in the power set of the empty set. So let's do one more. Let's do the power set of the power set of the power set of the empty set, which is just the power set of this thing. Here's where I would really encourage you, pause the video, try it, and then watch me do it. Did you try? You should have 4 elements in your answer. And these are the 4 elements. Just to make sure we see, that's 1, that's 2, that's 3, and that's 4. So we can describe the power set in terms of which of the elements of this set with 2 elements are there. If neither of these elements is there, I get the empty set, which is saying it's the set with nothing in it. If only the empty set is there, then I get the set of the empty set. If only the set, the empty set, is there, then I get the set whose only element is the set whose only element is the empty set. Which, yes, again, is a different thing from this. And lastly, it could be that both of these things are in my subset, in which case then I get just that set again. So power sets are going to be a very useful tool when we're talking about the sizes of sets and thinking about how all of the subsets of a set are related. Now, with the hope of making this as exciting as possible for you, I'm going to write down one statement at a time about power sets, and I want you to decide if that statement is true or false. And if it is true, then prove it. So, look at this sentence. For every set X, the power set of X is none-empty. Think for a second if you believe this is true or false. If it's false, what's the counterexample? If it's true, what's the proof? In this case, this statement is true. Okay, and so for the proof here, I'm going to suppose that X is a set. And what do I need to prove that a set is none-empty? Well, I need to prove that it contains an element. Well, what's one element that is definitely in the power set of X? And so there are 2 answers here that you could give. So let's do the confusing one first. And so, since the empty set is a subset of X, that tells us that the empty set is an element of the power set of X. And thus, the power set of X has an element, and so it's not the empty set. Again, note, the empty set is a subset of X, which makes the empty set an element of the power set of X, which means that the power set of X is, perhaps somewhat ironically, not the empty set because it contains the empty set as an element. Now, just in case you absolutely hate this, I can write down an alternate version for you that involves less empty sets. Well, what else do I definitely know is a subset of X? Well, X is also definitely a subset of X. And since X is a subset of X, that tells me X is an element of the power set of X. And so, again, since the power set has an element, it's not empty. So these proofs are almost identical, but in this one I used X as the subset to maybe make it read slightly more clearly, so that we don't have to think quite as much about all of this business with the empty set. Now read this statement, think about it, decide whether you believe this is true. Is it true that for every set X, X is a subset of the power set of X? You might think about whether that's what we just said or not. And once you've decided, I will tell you that this statement is very false. In fact, if you look back at our 1 to 7 example earlier, here's the power set. And note, the set 1 to 7 is not a subset of this set. What is it? It's an element of this set. Namely, it's here. So this is not a subset of the power set. It's an element of the power set. If this was a subset of the power set, what would that say? That would say 1, 2, and 7 are elements of the power set. But that can't possibly be true, because every element of the power set has to be a set, so it definitely cannot contain the elements 1, 2, and 7. Okay, so here you would write something like the earlier example to show that this is false. Okay, but the true thing, just to be clear, is that for every set X, X is an element of the power set of X. So this is the true one. So this is just good practice to make sure you juggle through understanding the difference between being a subset and an element of something. How about this one? Is it always true that actually the set X and the power set of X have no elements in common? So if you look back, for example, to this one, this is definitely true for the set 1, 2, 7. Namely, the set 1, 2, 7 has no elements in common with the power set of the set 1, 2, 7. Again, because all of the elements of the power set are sets, and none of the elements of X are sets. But if you look down a little bit further, you'll see that we have these weird examples where, for example, if I look at this set to be my X, then the power set of this set actually contains this as a subset. Let me show you. And so, in this example, which we did earlier already, the power set of X consists of these 4 elements. But then what does X intersect the power set of X? Well, in fact, every element in X is also an element of the power set of X. So, in fact, the intersection here has 2 elements. So you can cook up really weird examples where this statement is false. However, in order for this statement to be true, what has to happen is that the set X has to have the very unusual property that it has something which is both an element of it and a subset of it. And so in this instance, that something was the empty set. It was both an element and a subset. And that almost never happens. And so I'll go ahead and make a note here that this is false in general, but this is true for, and I'll put in quotes, reasonable sets. And there's maybe not a precise definition of what I mean by reasonable here, but you're unlikely to stumble across a counterexample to this in the wild. You're probably going to have to cook it up for yourself specifically because you want to think about something weird like this happening. Here are 2 things about how the power set interacts with cardinality. Namely, what happens when you take the power set of a finite set? The cardinality gets bigger. And what happens when you take the power set of an infinite set? Well, it is still infinite. Both of these are true. Let me show you how the proofs of these go. So let's start by supposing A is finite. Thus, the size of A is a non-negative integer. Note the reason 0 is included is that maybe A is the empty set. Who knows? And so we've said here, A is a finite set, it's got n elements, and hey, these are my n elements, x1, x2, x3, up to xn, however many that is. Now what do I want to show you? I want to show you that the power set has more elements. Namely, it has more than n elements. So really, what do I have to show you? I have to show you the power set has at least n plus 1 elements. And here are what I'm going to take my n plus 1 elements to be. The singleton set that contains x1, the singleton set that contains x2, all the way up to the singleton set that contains xn. That's n elements. But I could also take the empty set, because that's in every power set. And so this is a list of n plus 1 elements of power set of A. And so the power set of A has at least n plus 1 elements. And so the size of the power set is strictly greater than the size of the set itself. Preview for much later in the course. When we eventually make sense of what it means to talk about the cardinalities of infinite sets, our big payoff will be to prove that this statement is actually also true for infinite sets. That is, even if you start with an infinite set, in a weird sense to be determined later, the power set is still an even bigger infinite set. The proof, though, will be much more complicated than the proof we wrote down for the finite case. So, next up, we are meant to prove that if we start with an infinite set, at the very least the power set is still infinite. That we didn't somehow accidentally start with an infinite set, take the power set, and get a finite set. So what is A being infinite buy us? It buys us a non-terminating, non-repeating list of elements of A. So what do I need to do to show that the power set is infinite? I need to show that there is a non-repeating, non-terminating list of elements of the power set of A. And so the question is, how do I turn this list into a non-repeating, non-terminating list of elements of the power set of A? And so there's a few different ways you could proceed here. One is to just put set brackets around each of these. I'll do it slightly differently, where I'll take the subset which contains the first element, then the first 2 elements, then the first 3 elements, then the first 4 elements, and so on. And that will give me a non-repeating, non-terminating list of elements of the power set of A. And thus, power set of A is infinite. Last of these, let's say I take 2 sets that have no elements in common. That's what this A intersect B is equal to the empty set means. In the parlance, this would be A and B are disjoint. That's the word people use to describe this. Does that tell us that the power sets of A and B are disjoint? And so it might help you to do an example here. So if A is the set 1, 3, B is the set 2, 4, what is the power set of A intersect the power set of B? Well, you write out all 4 elements of both of these, and it's not so hard to see that it is that. That's right. These 2 things do have something in common. Namely, they have the empty set in common. And so their intersection, as painful as this is to say, is not the empty set. It is the set the empty set. And so as written, this is false. And this thing I've written here is a counterexample. Now, I won't prove it right now, but in fact, actually, if A and B are disjoint, then you can prove that the power set of A intersect the power set of B is, in fact, always the set the empty set. That is, if I put 2 little braces here, this statement goes from being bogus to being correct. Now, it's time for our first theorem about power sets. And the theorem I'm going to give you is the size of the power set. And so what does this theorem say? This theorem says that if A is a finite set, then the size of the power set of A is 2 to the size of A. Now, whenever I call something a theorem, I am telling you that this is a thing that could be proven. I may or may not provide a proof depending on the particular thing we're talking about. In this instance, I'm going to omit the proof, but if you want, you can search for there is a proof by induction that you could readily understand, But I think the more natural proof of this involves sort of counting principles, so we can talk about that later when we talk a little bit about counting. But from here forward, I have written this on the sheet of paper, and therefore, for the rest of the course, you are welcome to use the fact that if A is a finite set, then the size of the power set is exactly this. And so, for example, we did this earlier. When A is the set 1, 2, 7, then A has 3 elements, and we saw that the size of the power set in that instance was 2 cubed, which is 8. Again, what does this theorem say for infinite sets? It says absolutely nothing about infinite sets, because the hypothesis here is about finite sets, and so if the set is not finite, this implication does not tell me anything. So that's our introduction to power sets. In the next video, we're going to talk about another set operation, which is the Cartesian product. But that's all for now. I again hope you're having a happy new year, and I'll see you next time.